you can all hear me. Let me just try to share my screen with you. Okay, hopefully you see the presentation and you can hear me.
Yes, Gabriel.
Great, super. So first of all, many thanks, as already mentioned by Eric, for taking the time to be here with us and to discuss. I know it's quite it's quite challenging to try to make a presentation from I don't know 35 centimeter screen, and to try to have it also a little bit interactive. The objective today of this training, and those that will come as well, is not necessarily to take you through all the equation, but rather to guide you, to propose you some ways, some direction to look at the task, how to look at the task when speaking about comfort, and to try to give you more of a holistic approach. Therefore, kindly ask you when you have questions to help me, because sometimes questions also help the presenter, even if only just to take some air and to breathe a little bit. So few words on comfort. Hopefully it will work. Yeah. Okay. So now we speaking about comfort, and I wanted to share with you this this presentation, these images, because basically when you speak about comfort, you can understand so many things. You can speak about comfort and you think, well, you can think about winter, as Professor Arnio was saying, minus 22 degrees in Finland. It's not very comfortable to stay outside in a t-shirt in minus 22, unless if you are really used to it, but still. But it can be also like Nada could tell you what it means to have comfort at 40 plus 45, or maybe sometimes even 50 degrees. So this is speaking about the extreme of the temperature, but it's in the end, it's not only about this. A good part of the comfort has to do with the eyes and with what we perceive. How do we look at? Is it comfortable where I'm working, or is it comfortable from image point of view where I'm learning? I would add to this as well. Sometimes comfort is about trying to sleep in a hotel room when the ventilation is working very loud, and maybe some of you can do it. Me personally, sometimes I'm having trouble trying to sleep when the ventilation it's working, and as a result, you can always shut it down. But if you are in countries which are extremely hot, if you turn out the ventilation, you will find yourself waking up in the morning, wet soaking, because it's already 29 or 30 or 31 degrees in the room. And last but not least, comfort is also about being able to breathe, if you wish. Being able to breathe without inhaling all the noxies, or without having this dizziness and so on. So these are just few examples, because in the end, comfort is more linked to each and every one of us. Now, there are several definitions of what it's also healthy home. I've taken the liberty here to present a slide from the World Green Building Council. So you can see here, well, we speak about materials, good materials that take care of the indoor air quality. Then you speak about sound insulation. Then you can speak as well about light, about optimizing the access to light for the inhabitants. Then you link this with windows, which can maximize, or which are designed to maximize the view to allow for some natural ventilation, if it is the case, then of course you need to ensure that there is that you avoid moisture issues, that you don't have molds grow or you don't have damp. And last but not least, if you want, you need a chromatic approach. So pretty much in the same direction, definitions are somehow converging. Now, everybody is speaking about the comfort, but the question would be, why do we speak so much about comfort? Well, feeling good is not just desirable. It's needed because it also has an impact on the way that the human body is working. There are so many medical researches and all kind of other researching showing that if you feel good, if you have access to a certain level of comfort, then you can think faster. Or if you speak about in terms of productivity, you will process calls like you can see here in this report also from the Green Building Council, up to 12% faster. Or if you think about having access to light, to outside view, there are some interesting studies showing that patients will have a shorter stay by a factor of 9%. Just imagine at the scale of the sanitary system, what it means that all people which are in a hospital for a certain period would be allowed to go home with I don't know, 1, 2, 3 days faster than normal. Then there are plenty of examples. I will show you some others linked with higher results in scores in tests and so on, with productivity and so on. So it's not that we desire this, but it's also needed. It's a question of how the human body is designed to work, if you wish. Now, within the scope of the competition and within the scope of what we call comfort dimension in Saint-Gobain, we focused on 4 dimensions. One is linked with the feeling, it's the thermal comfort. The second one, it's linked with visual, with seeing, and it's part linked with visual comfort. And then the last 2, one it's the acoustic comfort, and the other one it's linked with the indoor air quality, or if you wish, we can call it indoor air comfort. These are the main 4 dimensions that we look at it, and about these 4 we will try to give you some ideas, some hints, some direction, which in the end would serve you in the way that you think about this project and the way that you look. The final touch, it's yours. The project would represent the way that you interpret this, that your mind was thinking about these dimensions and about the comfort in general through or for the well-being of the people that will live in the dormitories that will design, or the people that will come in this renovated building that you will design as well. Now, thermal comfort. Thermal comfort most of the time, or at least in our part, and when I mean in our part, it's continental Europe, is most of the time linked with cold. Yeah. You have a minus 10, minus 15, minus 20, even more in some cases. Then you need to ensure that the temperature inside the house, inside your construction, your building, your office, whatever, it's comfortable. But it can be also the opposite. It can be the comfort during the summer. And lately, the summer comfort has become was scrutinized even more because, well, if I may say so, in the winter you can always put a jacket on. In the summer it's more complicated if it gets really warm. Then there are some studies showing the effect on work performance. Yeah. Now you can see here some studies. This is from Brehwa journal some years ago, and you can see here the situation in the summer and in the winter. Yeah, this is in the winter. You can see it here, and here it's in the summer. And well, there are several curves, but in the end, you can see that in the winter, as long as the temperature sits somewhere between these two values, 20 to 24, 25, let's say, the relative performance of the body is really higher or the highest, and it starts to go down if the temperature gets either really high, which is less possible during the winter, or if the temperature gets low. But also you have the same effect, and it's slightly more abrupt in the summer. In the summer, if you are at 27 degrees, you can be around here, maybe 28 degrees in a building where the ventilation is not designed well. And then you will have as well this decrease in the performance of the body, because basically the perceived thermal comfort has direct effect on how the human body will work. So it's not that you want it, that we desire this, but it's also needed in order to work, to perform in good quality. Now, okay, what does this mean, thermal comfort? Well, it has to do with the air temperature. It has to do as well with the surface temperature. You can heat a room, but still, if the windows are really poor, and you go and you put your shoulders close to these windows, you will have this effect of chilling, and it will not be comfortable as well. It has to do with the humidity and so on. So if I would summarize it, the idea is that you keep the temperature within the good region, using as little energy as possible. Then it's good to have surfaces that are really pleasant when you touch them. And then it's good to avoid this drought even at the floor level. And then, okay, there are many solutions that you can choose from some sun, but then starting with glazing, continuing with insulation, with plaster and plaster boards, with membranes to improve the air tightness and manage the moisture and randoms. Now, few words about visual comfort. About visual comfort, well, the eyes, they will perceive it, and when you design, you tend to think with your eyes, because this is the first impact that you will have. You will see the space, you will see the building, you will perceive the light, the colors. So there are so many evidence about visual and visual comfort and the connection to light, and how good and important it's the light for the human beings. If you wish, I remember this very old Chinese, I believe, proverb or Chinese saying, stating that in the house where the sun does not go through the window, the doctor will enter through the door. And then you can link this with many evidence showing that if you have access, if you want, here there are some examples for schools, you have access to, if you give good access to light, then the results, the possibility of the children to learn will increase, and the body will function better, and as a result they will have either better performances, either faster progress on all kinds of tests, as math or reading and so on. And this is just only few evidence. As well, speaking about visual comfort, you can think about the view outside. So it's quite important then you allow the workers, the people that will inhabit the space, to have a view outside. The quality of the light, of course, and the luminosity, the absence of glare, and in general strive for having as much as possible natural light, as much as possible without a glare. Try to have rich colors, and well, if you wish, in a matter of speaking, try to bring the outdoors inside. You know? And here again, you can find many solutions within Saint-Gobain portfolio, starting from transparent product to translucent one, speaking about opaque interior products and so on. Then another important dimension would be the acoustic comfort. And we speak many times about it's important to have quiet, and maybe it's also important to show a little bit why. Now you can see here, this is a report from France, so it's a DIM, and it has monetized the cost of the social cost of noise in France. I believe this is done in 2018-17, and at that time the estimation of the cost of the social cost of noise was around 57 billion euro a year. This is basically the cost of noise in France, and you will have similar figures almost everywhere in Europe, or not almost, but everywhere in Europe. Then this is linked with the fact that noise has several adverse effects on human body, starting with high blood pressure, mental stress, and ending up with heart attacks, hearing damages, and so on. And we'll speak a little bit further about this in the acoustic presentation. And then, you need to take care about the noise from the outdoor, or you need to take care about the noise from the neighbors. You need to take care of the noise which is propagated through the building structure. If you live in a multifamily building, and the building is poorly insulated, you will definitely know if somebody is having some kind of impact action at the higher floor, I don't know, preparing some kind of schnitzel or whatever. You will feel it at the lower floors as well. Then last but not least, and this is also very important, it has to do with the clarity of hearing, with the speech intelligibility, to be able to listen what the teacher is teaching, if you wish. Again, many of Saint-Gobain solutions here can provide you with the acoustics. There are solutions from plasterboard, solution from insulation, acoustic ceilings, and so on. So all this part also linked with acoustic comfort. Last but not least, we speak about indoor air comfort, indoor air quality, if you wish. And here also you can see a short resume of the impact of CO2 concentration on the way that the people take decision. This is a study from Berkeley Lab, and it summarizes the way that the CO2 will impact the decision-making performance. Here you can see in the green we are around 600 parts per million CO2 concentration, so about 2 times, if you wish, the standard concentration which you can find in the outside. Then you can see already that the more I move towards higher concentration, which are very often found in the buildings, if they are not very well designed from this point of view, the human performance will be very, very influenced about this, yeah? From actions linked with basic strategy or basic activities or here initiative. You will find that the human body, it's unable to react in the right way. So we'll speak a little bit further about this also in the indoor air quality training. So indoor air quality, fresh air, and plenty of solutions that you can choose from Saint-Gobain. Now, if I sum them up, and again with some other examples, if we speak about thermal comfort, yeah, you can see here that there is a reduction of the performance by up to 6% in case of overheating. So just imagine yourself designing, I don't know, an office, and then not thinking very clearly and very, very sharp about overheating, and you just have very high temperatures. Yeah, the amount of the percentage of lowering the performance of the workers, if you translate it in money, it's impressive. Then you can have here you can see the increase of the productivity, and when I mean here productivity can mean everything from being able to screw faster or to I don't know, to work something manually, up to learning curve. Yeah, it goes up almost by 20%. And then you have as well, if you speak about poor indoor air quality, yeah, decreased by 10% of the performance, or if you wish, here it's about the offices, about 65% of the people working in an office, they will be distracted by too much noise. So putting this together, you can have a better image of why do we speak about comfort. And it's not only one dimension. You need to think about them as a whole, as a holistic approach. Also something which I think deserves a few moments here is just to introduce it briefly, and we will discuss a little bit further about them. These 4 dimensions, they are interconnected. Yeah? They are, when you choose to work on one, you need to take care of what happens also with the others, because the connection between them, they are very strong. So just think about the fact that, okay, I work on the thermal comfort, I design a house, I think about a construction that its aim is to have thermal comfort, and I will make it very, very tight, yeah? Just to avoid any losses of energy. And then if I make it very, very tight, then all the air gains that I was having through all the cracks and all the unetantiality of the building, they are no longer there. And suddenly I am stuck in a house which is very well designed thermally, but which will be extremely poor in terms of indoor air quality. Then the owner or the inhabitants will say, no, now I have to do something. I have to have very good air. And what he will do, he will just drill some holes to put a ventilation system, or he will open the windows all the night and all the day just to have some fresh air. Needless to say that the air outside can be polluted with all kinds of substances, so it may be better to have a ventilation system in some cases than to have this natural ventilation. But still, if I do this, then I might find myself in the situation in which I'm speaking about an apartment. This apartment is at a higher floor on a very busy street where I have, I don't know, a tram, where and the tram starts working at 5 o'clock in the morning, and then each day I have to choose. If I open my window, I will, or each night, I will woke myself with the noise of the tram, or if I don't do it, I will have a very poor quality of the indoor air. So they are all linked, and we will discuss a little bit about this as well. And also within the scope of the project, because in the scope of the project you have the sustainability as a whole, you need to think about using products which are having EPDs or which are EPD verified, which are products with environmental product declaration or systems, if you wish. This way, not only that you know the performance of the product or of the solution, but you are fully aware of the impact from CO2 point of view. So you can see that they are linked. It's not working on one and disregarding the other, but you need to work thinking about the approach as a whole. And then just to give you some examples, if you choose correctly, for example, in case of a building like this, which is a office building, and you go from what we generically call a low E glazing to, for example, in this case, a Saint-Gobain solar control. Not only that I will have a very good and balanced daylight autonomy, which means that through the year I will have more than 70% natural light in a quantity of 300 lux, as you can see here. But also, if I design it correctly and from the beginning, I will be able to decrease by 3 liters the consumption of oil needed for heating. I will be able to decrease it with 3 liters per square meter and per year. This is just one example. And then here are some examples about acoustic comfort and thermal. I will come to this in the next discussion, as well as for indoor air quality and comfort. Here you can see an acoustic treatment, on the ceiling, but all of these treatments, they are realized with a product which has an active air technology, which means that basically the product that I'm using there will help me, will support me by soaking all the VOC which are emitted in this area and supporting me having a very good indoor air quality. So it's always a question. It's always a question of looking, broadening your view and trying to think from different perspectives. So then, when you choose a product, you ensure that that product supports finally the sustainable approach, the thinking about different comfort dimension. And yeah, we have this, and that's why I put them together. We have these four sensorial comforts. You have the feel, the seeing, the hearing, and the breathe. But also you need to think in terms of energy and carbon. You need to think in terms of material and resources. And last but not least, you need to think in terms of health and safety, because they are basically the face of the same coin. On one hand, you think about comfort. On the other hand, you need to think about sustainability. We need to design energy for using as little as possible energy and emitting as little as possible carbon. Yeah? You cannot have one without the other. They do not work, and human beings will strive to get the one that it's missing. That would be the introduction part. I'll just okay. Any questions so far? First of all, did you hear me up to now? Because I was kind of in a cave, you know.
Yes, it was okay.
Yes, okay.
Yeah, it's
Good.
totally clear.
Okay. Any questions? I'm popping up for question, and I'm striving to get some questions from the students to see if all it's clear. Then we need to sit 1 more hour and discuss about it. No questions? No?
It's a sort of a further illustration, if you possibly can give me. Hello there, this is Iyad speaking from Ajman University. I would like to ask about, is there like sort of a formula or, you know, a combination between many components in order to confirm that all of the people are going to be matching or meeting this thermal comfort happily without impacting anyone negatively? So, you know what I mean, all of the components. So what is that best sort of 1, 2, 3 formulas: humidity, lighting, luminosity, and the temperature, etc.?
Thank you for your questions.
Thank you.
So one recipe to include all, unfortunately, no, because we are all individual. There are some, however, there are some directions, and we will speak, and I will try to pinpoint, not all of them, but at least few, from all points of view, from thermal comfort point of view, from acoustic point of view, from daylight point of view, from indoor air quality, and last but not least, thinking about sustainability. In the end, the task as such has presented you with some requests as well, because within the task you will find, when we speak strictly about comfort, you will find already some hints about some specification that the building has to meet. On one hand, you have some request link with the building itself. First of all, you have mentioned there the request for heating, energy used for heating, and that's around, if I remember correctly, it's about 15 kilowatt hour per square meter in a year. So you have to be below this. This is a building which is very energy efficient. At this level, you can start thinking about making the building positive in terms of supporting it with some active systems to generate energy. This is one point. As well, you have within the criteria another one which says that the building has to have a certain level of air tightness. That's, if I remember correctly, 1.5, the N50, which is basically telling you that the building will exchange with the exterior about 1.5 times the total volume of air inside the building through cracks and openings other than those those designed for it. I mean, it doesn't take into account the ventilation, or it doesn't take into account what happens when you open the windows. So this is also linked with the building. And another thing which is very interesting as well, although we are in Poland, and the tendency would be, okay, in Poland, what do I know about Poland? It can be sometimes quite cold. The specification is that the design should strive to provide summer comfort, because it mentioned there, try to provide it without air conditioning, which means that within the global design, the students, the participants should take a look, I would say, also on what happens in the summer. If I have extremely generous windows towards south and I have no shading, I should question myself, will this impact in any way my comfort? And then there are some specification linked with the opaque elements, or with the windows as well, where you have a U value or R value for the walls and so on. This issue, if you put this specification, then for sure you will have a very nice wall to touch, and you will not have all these kind of issues. And then, well, the training, as it was already mentioned by Eric, it goes through the 4 ideas, but I will try to make some interconnection with the different ideas so that we can speak more precisely about them. Now, within the coming slides, I will try to talk with you a little bit about summer comfort. Please, because this is also helping me, if you have any questions, feel free to stop me. And thank you for the question, and I'll dive back to the presentation in 1 second. Now, can you see it?
Yes.
Great.
Yes.
Super. So, well, the buildings are part of the problem. Yeah, definitely, we consume about 35, between 30 and 40% of the energy. We consume it to heat or to cool, depends on where we are. And then you have about 35% of the CO2 emission, which are, of course, the result of this. So just think in terms of global image, how many buildings we have. Well, from this point of view, the buildings are a problem. On the other hand, they are as well a solution, because if by miracle tomorrow we would be able to get all the buildings from the levels which we have today, at which they are today, I don't know, consuming 200, 250, 300 kilowatt hour per square meter in year, and decreasing them to, let's say, 15, like we have in the task, then you have a 95% decrease, which means that out of this 33% or whatever, 35, you name it, I would be able to go down 90%. It's a huge impact, and it's an impact that we can do it. Of course, you need to work on 2 directions. You need to work on renovation, and you need to work on new. And of course, this is why also the task is challenging and beautiful on the same time, because you have a new construction where you can do whatever you want. I mean, you can open your mind to integrate without borders, but also you have the renovation part where you have to think a little bit about what is there, what is existing. And this is pretty much like in life. Now, we were speaking a lot about this comfort, and basically, if I'm looking at the climate zone of Poland, then I know that my temperature will evolve in the summer, and in the winter I will have very high temperature in the summer, yeah, and even and not nice temperature in the winter. Now, there are two curves. The curve in red, it's representing the inside temperature in a poor insulated building, and the green one, it's a curve that will show you how this temperature evolves in a far better insulation one. So you can see here that if I didn't design it from thermal point of view, I will need to decrease a lot the temperature during the summer. That means that I need to put some chilling, some cooling solution there. I will consume a lot of energy, but also I will need to do the same thing in the winter. Yeah? Now, if I manage to get my temperature within this area of comfort, then basically the consumption of energy for being in the comfort zone will decrease dramatically, and that's how I can lower the consumption of energy, and of course decrease the emission of CO2. Now, there is a very nice movie that I would like to share with you. Just allow me 1 second. Okay, I have it here. Hopefully, and please let me know if you can hear as well the sound, yeah? You can hear the sound? Yeah?
No, we can't.
Oh.
No.
Moment.
I guess
So,
you have to reshare your screen.
yeah, no worries. No worries. I will do that in a second. So, let me see. Maybe now.
Early settlement began in mild climates.
Can you hear it?
As man moved north,
Yes.
developed different kinds of shelter to be comfortable through the changing seasons. The building environment, which acts as a filter between the inside and the outside, gradually became more sophisticated. During the 20th century, we gained unprecedented control over our thermal environment, mainly thanks to energy-consuming equipment such as central heating systems. As we advance into the 21st century, world population, the percentage of urbanized areas, and expectations of comfort and well-being continue to grow. Striving to reduce energy demand of buildings while providing comfort and well-being requirements is more important than ever. Designing efficient building envelopes is one of the first steps to consider. Today, we spend more and more time indoors, where we expect a level of thermal comfort that ensures comfort and well-being, but can be provided efficiently. While extremes in temperature can be fatal, even gentle fluctuations can cause us increased pleasure or discomfort. Concentration, manual dexterity, and instances of accidents can be influenced by both high and low temperatures. The basic principles behind thermal comfort are largely universal, but thermal comfort varies from one person to another. The physiological aspect of thermal comfort. Human bodies, as with all mammals, are thermal engines that generate and dissipate energy. We have different ways to balance our constant heat exchange with the environment. For example, by shivering, perspiring, or modifying our blood flow to regulate heat distribution. The objective of our metabolism is to regulate our body temperature with minimal effort, if possible. So we need to be able to control the physical environment surrounding us. The physical aspect of thermal comfort. Thermal energy, heat or cold, can be transferred by three means which influence our perception of the environment. 1. Conduction is energy transferred via a solid, for instance by touching a surface. 2. Convection is energy transferred from a solid to an adjacent gas or liquid. 3. Radiation is energy emitted from a surface. An overall balanced thermal environment is key to feeling comfortable. But our bodies are very sensitive, and local variations within our environment can cause great discomfort. For example, sitting too close to the fire, or by an open window on a cold, windy day. The socio-psychological aspect of thermal comfort. Many other factors influence our perception of our thermal environment. Our current emotional state, mood, or how tired we feel. Our thermal programming and social background. As well as other environmental factors such as noise or glare, which can make us agitated and feel hot. Our perception of heat also depends on varying tolerance levels. For instance, the more control we have over our thermal environment, the better we feel and the more productive we are, whether or not we choose to use this control. Designing for thermal comfort. There is no one-size-fits-all recipe for thermal comfort. Solutions vary depending on the local climate, as well as the type of activity performed by the building users. The building envelope acts as a filter between the exterior and interior climates. Designing it efficiently implies the consideration of 5 main factors. 1. Insulation reduces heat loss during cold seasons and heat gain during warm seasons. 2. Solar gain is influenced by the building's insulation levels, its shape and orientation, the window to opaque wall surface ratio, the type of glazing, shade or shading devices. 3. Thermal inertia varies according to the mass and material of a building. High inertia envelopes give more internal temperatures in the face of outdoor temperature change. 4. Air tightness and ventilation enable the control of air exchanges with the outside. A well-designed building envelope can dramatically reduce the need for mechanical systems required to provide thermal comfort, so reducing the environmental impact. The future. Although our basic thermal comfort requirements are likely to remain the same in the future, our outdoor environment is likely to change further. Climate change will play an increasingly important role in the design of the built environment. New systems and materials will continue to be developed and refined. These changes, as well as a new approach to energy use, will require buildings to be capable of evolving over time in order to be both comfortable and energy efficient. A key factor in this evolution will be to ask ourselves what levels of thermal comfort will be considered acceptable. Should we just put on a jacket rather than turn up the heat?
Yeah. That's an open question as well. What will be the level of thermal comfort in the future? How humans will react to this in the future? Because this is also a question open for the interpretation of the participants, because you can think this from the both perspectives. You can think, okay, I'm designing, looking at this, I did the maximum which I could do, but it's also something that the humans need to take into account, human beings as such, need to take into account as humans themselves. Now, we were seeing here some of the main criteria. You can see still the presentation, yes?
Yes.
Good. So, when it comes to the variation depending on the local climate, we know for sure that we are in a European moderate, cold moderate climate. We know also the activity that will be performed there. So though we remain with some ideas that we can discuss. First of all, we are looking at the envelope. Yeah? So we need to treat the envelope in order to ensure that during the winter I have pleasant temperature inside, that it doesn't get too cold, and also during the summer, sorry, I ensure that I don't have too much heat. Then once I have worked on this, I can think about the second step, which is the solar gains. Or link with this, it's the way that I'm going to organize my building, the way that I'm going to design it towards the cardinal points, then the type of the glazings and how much I will make the glazings. Yeah. And then you can look at we can look as well as the thermal inertia, and we can look as well as the air tightness and ventilation. And this part with the air tightness and ventilation, it's, in my opinion, it's linked also with indoor air quality, and I will discuss a little bit about it in the second session of within the second session of indoor air quality. Now, coming back to what we were discussing, we know that a well-designed building envelope can dramatically reduce the need for mechanical systems. That's also our aim to ensure that by the envelope itself, because this is the first step, I decrease as much as possible the need for mechanical systems, independently of what the mechanical system is. Can be the central heating system. Yeah, I design it in such a way that I need only few amounts of energy to keep it cooler in the summer or hotter or pleasant in the winter. Now, if I speak about this and the usage of energy, this is a study which was done some years ago. The question was, they were asking people if they have an idea how much of the energy that they spend, it's used on different things. And you can see here on the right side, I would say the consumer's opinion. Yeah, so the perception was that we use a lot of energy on the electrical appliances, that we use, of course, a lot of energy on heating, but also a lot of energy on hot water. Well, in reality, the values are quite different, if you wish, because if you look at in terms of heating, it's about twice as much. If you look in terms of cars, we use about twice as much in reality. And then the electrical appliances as well as the hot water, they do not represent that much in the overall picture. The overall picture would look a little bit like this. Yeah, it's a space heating and cooling. It's the main energy consumption in residential building. And if I'm looking at the European moderate climate, roughly around 75% of the energy is used for heating and cooling. If I go more towards north, it will be heating, almost not at all cooling. If I go, I don't know, on Spain, on South Europe, then I will have a little bit of heating, but I will have a lot of cooling as well. And then also you can see here, this gives you an idea on how to design. You can see here that light, the amount of light, if we speak residential, it's very low in the total consumption, as well as the household appliances. And I believe that figures are even slightly smaller. It should be slightly smaller because lately all the appliances are with higher, very high energy efficient classes, AAAs or AA's or whatever. So I need to focus, if I'm thinking in terms of being effective, I need to focus on the biggest consumption. The biggest consumption would be heating and cooling. Now, for us, we know that we are in Poland. It's a little bit more of heating and a little bit less of cooling, but still we have this specification, and you need to think a little bit about this as well. Now, the criteria that we were mentioning is this one. Yeah, it's in the contest tasks, and you need to reach an annual energy demand for heating below 15 kilowatt-hour per square meter in year. Now, if I look in terms of well, how much is it? 15? Is it a lot? It's normal, or what is it? You can see here a graph which is saying, okay, this is let's say a building stock. This is a building of the 90s or 2000 if you want. This is a low energy house around 50, and then your target would be to reach this one. So it's an, if you wish, a nearly zero energy building. We can say it this way, and building with energy consumption very low, and which could be easily supported by active measures such as putting PVs or any other kind of active energy generation. And then as well, just to give you a link with what it means. Yeah, if I speak about the existing building stock, then we are at values of 300, let's say 250 kilowatt-hour per square meter a year. And my objective with these very low energy houses or nearly zero energy houses would be to go towards a consumption of 15 kilowatt hours. And here, without having without being perfect or absolute true, but this is just for the exemplification. You can see as well what it means, yeah, in terms of insulation. If I'm looking here at the external wall and I say, okay, I have a massive wall of about 25 centimeter, then if I'm speaking about old buildings which were realized, I don't know, 30, 40, 50 years ago, there is no insulation. Maybe 25 years ago or 20 years ago, I was having 5, maybe 10 centimeter, then I would go slightly towards 16. And then if I'm looking of what I need to get to about 0.13, 0.15 watts per square meter Kelvin as U value, I would need approximately 30 centimeters of insulation. That's the filling. And then, yeah, you can also look at the windows here. Yeah, we know we have simple glazings, or many years ago, and then here you could think about double or triple glazing with a new value of 0.8. And then, of course, you have here some comments about ventilation, the ventilation was done by opening the windows. But then if I fully insulate the house, and I do all the things that I can do to keep the energy inside, maybe I find a smarter way to ventilate than to open the windows, because it's pretty much like I would have a fridge. Yeah, I have a very good fridge, but then I keep it open. It's pretty much the same principle if we wish. And then the more tight the building is, then I need to bring this air to be able to breathe. And if I'm depending myself on some kind of a system to bring the air, maybe I can somehow make a transfer of energy from the air that I have to take it outside to the air that I have to bring it inside. And this way, maybe I have some kind of a ventilation with heat recovery. And then, yeah, here you can also see the effect in terms of CO2. From 60 or maybe 30, depending on when the building was designed, I would go to what? About 2 kilos per square meter in a year. That's just to give you a rough feeling of where this criteria in terms of building it's positioning you. And this is generally the criteria that it's going out in Europe, because almost everywhere in Europe you have this nearly zero energy building legislation, which lowers very much the consumption that you need for the heating and cooling the building and for all the others. And on top of it, it brings active measures of generating green energy. Okay, and then this is also what I was mentioning. If I try to put active measures on this kind of buildings like this, it's like, well, I don't have the right word, but it is not effective. I'm consuming so much that I would need to produce a huge amount of energy, and I'll still need to invest a lot of things to do it. The right way, the smart way to do it is first look and decrease as much as possible the energy need through the envelope. And then whatever needs they remain, and these needs, they are linked with the comfort. I can either, support them to a net zero energy level, which means that my building will be zero energy building. I will not consume energy. I will not as well generate, but I can very easily go one step further and make my construction, my building, a generator of energy by using photovoltaic, if you wish. Now, how do I get from active heating, basically what we do, to preserving energy? Well, I think this image summarizes it well. And we keep doing it right now. Yeah? This is the way that we do, well, we used to, or we still do in plenty of parts. We do the coffee. I generated the coffee, and then this one, it's on, and it keeps the coffee warm. Yeah? The other way around is just a common heat, thermally insulated bottle, which keeps the coffee hot. That's pretty much all it is no fancy technology or whatever. And you can see here the infrared. Huh? This one shows nothing. And this is the kind of image that you should strive for in your buildings. If I transfer this image to a building, this is how it could, or how it should look. Yeah, this is a very poor insulated building. Yeah? You can see it bleeds energy, it bleeds heat all over. More at the structural things, which are here, here above the windows and everything else, here at the last floor. And here, it's more or less the same image of the same building after retrofitting. And you can see here in terms of the wall that the losses have been severely or very much decreased. Yeah, here there are some open windows tilted. Here you can see as well that there is some kind of ventilation which was put it in, and of course here is the open door. So we can say that the entrance door is not necessarily the most performant. But this is what you should strive for. This is the image that you should think about, and this is very simple to look at it. This is an energy audit which is done. Just take a picture or an infrared picture of the building, and you can instantly feel this building it's been well designed, or contrary, has not been very well designed. Now, if we speak about how do you get from active heating to preserving energy, well, we need to look a little bit on how do we lose the energy, or through which elements we lose the energy. So if I'm looking at a house which is looking slightly like this, then I'll have about 25% through the walls. I will have about 30% through the roof. Something will go through the basement. I'll have the windows, of course. I will have some air leakages, and last but not least, I'll have some thermal bridges which are influencing my losses. Yeah, and if I put this together, because I lose something, and then I need to ensure that this energy which is needed, I put it somehow back. And if I'm having on this side the losses, then on the other side here, and I'll just scroll in, I have the gains. And what kind of gains do I have in a building? Well, first of all, I can play with the sun. I can always get a lot of energy from the sun. Yeah, it's just a question of using it correctly. Then I also have some internal gains. I have energy, I gain heat from the people which are working, because basically each person is somehow like a small radiator. I can get energy from the computer. I can get energy for all kind of devices that I have it inside. And then I still have, in the end, a small quantity which remains. Well, this small quantity, the smaller I get it, the better it is. And this small quantity I can add it, I can support it by active measures or by taking it from the system. Now, this is from training many years ago, and then you can see here the standard approach which we have, pretty low performance in terms of insulation and in terms of windows. And then what we used to do is that we get the engineer putting here a radiator to compensate for the cold air, and to have this comfortable feeling. Then today you always have the possibility of insulating very well the building. Not only that insulated, but I'm ensuring that I am having very good windows. So this way the temperature on the surface of the windows is no more, I don't know, 9-10 degrees. It's more towards 17. So then I don't have this feeling of discomfort. And then last but not least, if I'm very well balanced, I can even think in some cases to support it by heating it through air, or if not, I can use some conventional systems like heating it through the floor or through the ceiling, but still the energy that I need for heating, it's decreased by a factor of 9. Now, I was mentioning that you have some specifications in the task. You can see it here. You have a U value for the roof, so it's just a question of getting a roof, a detail for roof which will respect this value. Then you have a U value for the external wall as well. You have also mentioned the U value for floors on the ground, so the floor on the ground for the building. And last but not least, also you have some U value for the windows. They are generic, they are given as direction. It's good to think about them and to have some kind of thinking, some kind of exercise. You can always contact your Saint-Gobain leaders or contest coordinators to support you with construction details from each country, or with general details on this. But it's good also to do the exercise yourself. You can see here one detail of a roof. If I look at it, I will just scroll down. Now my detail looks a little bit like this. I have a layer of 2 plaster boards. It's okay? Can you hear me? Can you hear me?
Yes, we can hear you, but someone is disturbing.
So I was saying that you can have a you have some plasterboards, then you have some insulation between and below the rafters. Then you have an air tightness layer, and this is important, and we'll speak about it. And then okay, you have the structure of the roof. As a general level, you can see here that this part, it's 5 centimeters, and then the insulation between the rafter, it's about 26 centimeters. So if I would sum this up, it's about 31 centimeters of insulation. And then also I would add that here you have a air tightness layer, which is going all around the house together with other parts that are ensuring that your building is tight. And okay, you can calculate this as an air, as a thermal resistance, but you can also calculate this as an U value, as a transmittance, and then it's the opposite. It's O equals 1 by R. The very straightforward equation. But this is just to give you an idea. You can always find on the website of Saint-Gobain, and there are plenty other of tools that can allow you to calculate the U value or the R value of construction. You can always find on the Saint-Gobain websites plenty of details where you will find these values as well. This is just to give you an idea of what kind of level do we speak. Well, yeah, that's one point, and then here you can see as well. If we speak about a wall, an external wall, here you have an attic system. This one, from here to here. So my wall, it's a wall of almost 20 centimeters, and on top of this wall I have added something like 20. Sorry, my writing is not perfect. 28 centimeters of insulation. and thus getting to an air value of about 8.3 and U value of about 0.12. Yeah? As well, you can see here that my airtight layer, which is this one here, is coming and it's continuing and it's linking on the wall, and on this wall my airtight layer is done with the plaster, because I have a layer of plaster which is ensuring this airtightness. Now, if we spoke briefly, and just to give you some ideas about the roof, the wall, and here again you will find plenty of insulation on the Saint-Gobain local websites, and if you have any questions, please address to your coordinators, to your country contest coordinators. Few words about windows. Yeah, windows on one hand, they need to be treated to ensure that there is lower the energy losses. And on the other hand, the windows, they can always play in your favor by allowing you to gain some energy. Now, first of all, when you speak about windows, you need to look at the light transmission. What it means? It means how much light will allow that window to penetrate. Yeah? The higher this index, which is an LT, light transmission, and its a percentage, the better it is. It means it allows more light to come into the building. Then you have UG. U stands for the transmittance, and then you have the G, which stands for the glass. So this is how well does the glass itself, the glass of the window, insulates, and the lower it is, the better it is, of course. And then you have the UW, which is the total value, the U value for the windows, taking into account the glasses and the frame. Yeah? So these two, or if you look only at the window, the lower it is, the better it is. And then you have the solar factor, which is G, and this G tells you how much of the energy it's transmitted inside. In other words, if I have a higher G, yeah, it means that a lot of the energy, a lot of the heat from the sun will come into the house. If I have a low G, then it will not allow that amount of energy, but a much lower amount of heat will come into the house. Now, here, it's good to have it as much as possible higher in the winter, because this way, in the winter, I get a lot of sun, a lot of free heat, if you want. But it would be ideal also that in summer, it should be as lower as possible, because if I'm already at 5 degrees, 26 degrees inside, and outside there is 34, 35, 38, it's a wave of heating. It's not good to have all that heat coming inside the house, because once it has come inside, I have very good windows. So it will not go out that easily. And here, this G factor, it's a constant one for the windows, it does not change. So you need to find a compromise to find the best solution. And if you look at the different type of windows, if I'm speaking generally about single glazing, double glazing, and triple glazing, you can see that, well, of course, the more sheets of glass you have, the light transmission is decreasing, but still if I am over 70%, then it's okay. If I am over 75, then it's even better. The UG, the how well insulating, how good does insulate this glazing of the window, it decreases from 5 to 0.6, 0.7, so you have a decrease of almost 10 times. And then you have here some standard G factor, solar factor, which is close to 1 in case of single glazing, and it in average it's about 0.5 to 0.62 for triple glazing. However, here you can have solutions from, I don't know, 0.3 up to, I believe, 0.7. So you have a much wider interval of choosing. Now, the way that you choose, it's up to you to decide and to think about it. You can play with the sun to reach a high energy performance in building. If I need to put windows on the north side, then in terms of energy balance, it doesn't help me a lot. But it can be that I need them just to provide light. So whenever I need this from thermal perspective, it's good to have a low U value, and if possible, not that huge amount of windows towards of glazing towards north. But I'm speaking here only from thermal perspective. Yeah? If because of the seat, if because of other constraints, I need light, I need to place my working spaces towards north because there is the view, then I do so because I need to think also about the visual comfort. And then I know from thermal comfort that I need to have it with a very low U value, and I dimension my windows taking into account my light criteria. If I'm looking at the south, well,
Gabriel, sorry, I played the timekeeper a bit. Just to
yeah, I know. I still have 3 minutes. I will stop this one here, and we will continue with the rest in the second part. There are still 3 minutes just to finish this one.
And there are a few remarks or questions in the chat also.
Yeah. Well, I'm just ending this one, and then we take the discussion. So. Then you can think about the south parts, and then in the south part you need to think about what kind of G factor we will put. You can put a higher G factor than you could have. You have to think about possibility of having overheating in the summer. If you put a lower G value, then you have lower heat gains during the winter. And I will stop this one here just to discard. To get a chance to go to the questions, and we'll continue this in the second part. And you were mentioning, Eric, that there are some questions. Let me double check myself as well. I'm not seeing them, but maybe. Okay, so well, I think. There are several. Well, Fatima, therefore in the room a natural daylight autonomy of 60% should be achieved. How can we analyze this sentence, and what exactly does 60% autonomy means? Well, we will speak about this, or you will speak about this tomorrow in the visual comfort training. There are several ways in which you can evaluate it. There are several There are several tools that calculate this daylight autonomy. In principle, the daylight, or not in principle, the daylight autonomy tells you that during 60% of the time that you define, let's assume that this 60% applies to a school. It means that during the learning program, which can be from 8 o'clock in the morning to 5 o'clock in the afternoon, in 60% of the time of the year, you have in average 300 lux natural light inside your room. This is the minimum. Basically, it tells you that you have the best amount, the best quantity of natural light in your room, which means that the higher you have it, the lower your consumption would be. And this daylight autonomy, it's an index that it takes into account also the geometry of the building. It's compared to the day factor, which is not. But we will discuss a little bit more with my colleagues from Glass about this tomorrow. I hope this question was, this answer was good for you, Fatima. Now, I know Professor Petri is saying that in Finland we use insulation in the roof about 500 millimeters, not centimeters. Or is it centimeters, Professor Arnio? Yeah, it's centimeters. 50.
50.
Yes, yes. Of course, well, you have to, as Professor Arnio was saying, you have to realize that in Finland sometimes it can go up to -40. And then 50 centimeters, it's a good answer compared to a 30 centimeters or 25 centimeters that you would request for Poland. Iliad, how good are the concrete building in such cold regions? Well, this is a good question. In such cold region or in warm region or whatever regions, the choosing concrete, it's not linked with thermal, because in terms of thermal properties, concrete is really poor. It's by a factor, if I am not mistaken, of 1 to 100 or 1 to 1000. I think 1 to 1000. So it doesn't help you at all. However, from many other reasons, such as rapidity, the traditional way of doing it, prefabrication, or if you wish, earthquake consideration, the buildings are done in concrete. The way to do this is to ensure that you have a proper insulated envelope. And if you think further in terms of sustainability, then maybe instead of putting, if you don't need it for static reasons, instead of putting 30 centimeters of concrete, maybe you can put only 15, and the rest of 15 you use it for insulation. Just imagine the amount of CO2 that you can decrease, because you are not using this concrete. Then average thermal handling on roof should be below 0.3. In Dubai, yes. Ideally, should be below 0.15, if you ask me. And also, ideally, in Dubai, you should have some light color, if possible. And there is, if you want in Dubai, it's an opposite idea. Here in northern part of Europe, you try to get heat inside, and make sure that during very hot summer, you keep it outside. In Dubai, is the opposite. In Dubai, you try to keep it outside as much as possible. So in Dubai, if I would have to choose, I would put, if I can get my light criteria correctly, I would put very low G glazing that allow very limited amount of heat to come, and I will make sure that I have some kind of shading. There are some slides and we'll discuss it next time, just to ensure that I do not bring any heat inside my building envelope. Then of course you have some questions about dehumidification and so on, but it's a different scenario. We had the chance of being in Dubai. Nada can support you with a lot of answers to your questions here. Is there a software that you recommend for us to use to simulate the heat gains and losses in the building? Well, we do not recommend one specific software because you have so many of them. Almost everybody almost all the software designers have some kind of a software. Almost all universities have some kind of I wouldn't say it personal, but their own calculation tool. You have other softwares available on the market. We said, okay, it's not about the result itself. It's to prove to your teachers, to your jury at the national stages, and as well as the international one, that you have thought about. Yeah? I'm pretty sure that nobody, and Professor Arnio, who is participating in the contest since I think now 12 years, if I'm not mistaken, can tell you that he will not look at the comma. Yeah? It's 0.131 is not correct. But it's more the way of thinking, the way that you embody these ideas and you put it in your design. If we have external connection like bridges, would it be an area where thermal comfort would be affected inside the building, where because of conduction the bridge would change the? Yes. Well, if you connect the bridge, to a building, of course you can do that, but then instead of thinking about this, maybe, and this is just one idea, you make sure that the part where you connected your bridge to the building is not part of the heated envelope. Yep. Basically, although it's as a scope, it can look that the bridge is connected to the building itself, in that part can be just the shell and not a heated envelope. So if you take this part out of the heated envelope, you solve much easier the question. Otherwise, it's a whole discussion about how to thermal insulate a bridge, which can imagine yourself a bridge. It's a big thermal bridge, it's not a small one. I'm not sure I have answered to your question, but I hope I did. I know Eric, it's pressed by the time, but well, if it's all for now, I would thank you for your time. I hope I did not use too much of your time and energy and resources. And I will see you in what, 2 hours, I believe?
Yes, it's at 2 p.m. Paris time. Yes.
Okay.
In 2 hours.
Good. Thank you so much.
Thank you, Gabriel.
Okay.
Thanks to all of
Thank
you.
you, Gabriel. Ciao.
Pleasure. Bye-bye.
Ciao.
Bye.